Hello student, how are you? I am Arunsir. Welcome to my channel Tuition Expert. Today in this class, I'll teach you thermodynamics. Student, in two class, I will finish the whole thermodynamics class with derivations, and this will be very helpful for your school exam, NEET exam, JEE Main and IIT. You don't require to see the another video. Student, if you watch my video regularly and follow my class attentively, then I can assure you that you must crack the IITJ exam and NEET exam confidently with a good rank. Now let's start about the class. So solid has one specific heat, but gas has two specific heat, because in solid but gas has two specific heat sp, but gas has two specific heat because in solid there is no effect of pressure on the volume, no effect of pressure on change of volume of the gas. So for the gas, both pressure and temperature affect the volume of the gas, but in solid container and here n mole gas is present, now we supply the heat, at here T1. Suppose T1 is initial temperature. Now finally temperature increases, temperature of the gas increases. Suppose temperature T2. Now heat supplied here Q. So if volume of the gas remain constant, suppose volume remain constant, this volume and this volume, here pressure P1, temperature T1, volume V, here pressure P2, temperature T1, suppose T2, and volume same, that is volume of the two gas remain same, temperature and pressure is changed. Now what is Q? What amount of heat supplied to the system? So if Q amount of heat supplied to the system, then we define specific heat at constant volume as heat required to rise the temperature of gas through 1 degree centigrade, heat required to rise the temperature of gas to 1 degree centigrade at constant volume is of 1 mole gas through 1 degree centigrade at constant volume is specific heat at constant volume, which is Q by 1 mole gas. Cv equal to Q by temperature rise T2 minus T1, Q by this, and if we take n mole gas, then we have to divide n. So for n mole gas, for temperature rise T2 minus T1, heat supplied is Q. For n mole gas, we can derive by unitary method. For n mole gas, for T2 minus T1 temperature rise, heat supplied is Q. Heat supplied is Q. Now for 1 mole gas 1 degree centigrade temperature rise. Now for 1 mole gas, for 1 degree rise, heat supplied is Q by N by T2 minus T1. So this is the definition of Cv. Cv equal to Q by N T2 minus T1. For small temperature rise, we get Q equal to n Cv into dt. Dt equal to here T2 minus T1. So this is the formula of heat supplied at constant volume. This is an important formula, Q equal to NCV dt. Now when volume is constant, then what is Q equal to Q equal to del U plus W. Volume is constant, means work done equal to 0, and Q equal to this NCV dt equal to del U. So this also another important formula. Del U, that is change of internal energy in constant volume at constant volume equal to NCV dt. This is the formula. Suppose here n mole gas is present, n mole gas heat supplied here. Here pressure, volume, temperature is P1, volume pressure P, volume V1, and temperature T1. Q is heat supplied to the system. So after supplying the heat, pressure constant, volume expand. So suppose here pressure, volume, temperature is P, volume V2, temperature T2. So after supplying the heat, pressure same, the gas expands, so pressure remains same, volume and temperature is changed. Now here what is the specific heat at constant pressure? Specific heat at constant pressure, Cp, is defined as heat required to rise the 1 mole gas through 1 degree centigrade of heat required to rise the 1 mole gas through 1 degree centigrade at constant pressure is Cp. So here to rise the temperature T2 minus T1 for n mole gas, heat required is Q. So for n mole gas to rise temperature T2 minus T1, heat required equal to Q. So for 1 mole gas to rise temperature 1 degree, heat required is for unitary method we can derive n by T2 minus T1. So this is heat supplied at constant pressure. So this is called Cp. So Q equal to n Cp T2 minus T1. Now this is QP, that is heat supplied at constant pressure, and previously we have discussed QV, heat supplied at constant volume, equal to n Cv T2 minus T1 or n Cv dt. So two important formula I have derived, QV and QP. These are very important to solve the thermodynamics problem. These are very important. So QV, QP. QV means heat supplied at constant volume, which is NCV dt, and heat supplied at constant pressure. Now Cp minus Cv equal to R. Very important formula, Maer's formula, called Maer's formula. Now we thermodynamics for constant volume. For constant volume, thermodynamic equation is QV equal to del U plus work done equal to 0. So QV equal to NCV dt equal to del U. This is equation 1. Now for constant pressure, QP equal to del U plus work done is not 0. Here work done equal to 0. but here work done equal to P into dV. So now del for both case, suppose temperature change is same. Temperature is changed for n mole gas, N1 T1 to T2. For both cases, temperature of gas increases from T1 to T2. So for both cases, temperature is changed same. So del U for both cases will be same. Del U will be same. So now for this, del U equal to N CB dt plus PdV. PdV, what is PdV? PdV equal to NR dt. Now Qp equal to what? Qp equal to this N Cp dt. If we cancel dt from both sides, N dt from both sides, N dt into Cp equal to N dp Cv plus R. So cancel this, we get Cp equal to Cv plus R, that is Cp minus Cv equal to R. This is called Maer's formula. Important here, Cp is molar specific heat. Molar means 1 mole. The specific heat for 1 mole unit is, I define Cp equal to Qp by N T2 minus T1. So this is calorie per mole per degree centigrade. Calorie per mole per degree centigrade. This is called molar specific heat. Molar specific heat. So molar specific heat is calorie per mole per degree centigrade. Now if we take the specific heat at gram calorie per gram per degree centigrade, what is the value? Calorie per mole per degree centigrade equal to, we know 1 mole equal to m gram. 1 mole of any substance equal to calorie per 1 mole equal to m gram per degree centigrade. So 1 mole equal to m gram. So if we define this Cv equal to calorie, then so Cp equal to calorie per mole into degree centigrade. Capital Cp is equal to molar specific heat at constant pressure. Now there are another specific heat, gram specific heat. It is denoted by small Cp, that is the gram specific heat. Now at constant pressure. What is the relation between Cp and small Cp? We know that we know that 1 mole of any substance equal to m gram. M is molecular weight. So if we define Cp, heat required to rise 1 degree centigrade of 1 mole gas. So heat required to rise 1 mole gas through 1 degree centigrade equal to Cp, capital Cp equal to Cp. So heat required to rise 1 mole gas. 1 mole gas means heat required to rise 1 moles means m gram gas through 1 degree centigrade equal to Cp. Now heat required to rise 1 gram gas at 1 degree centigrade equal to Cp by m. This is called small cp. So small cp equal to capital Cp divided by m. That is capital Cp equal to m into small cp. M is molecular weight. Gram specific heat. This is molar specific heat. We get Cb equal to m into Cb, small cb. Now relation between pressure and temperature at constant at adiabatic process. Pressure and temperature, relation between P and T. We know P into V to the power gamma equal to constant at adiabatic process. Now PV equal to nRT is the gas equation holds for any process. PV equal to nRT holds for any process. Now if we want to relate between pressure and temperature, we have to eliminate the volume. So V equal to nRT by P. If we put here V equal to this, we get nRT by P whole to the power gamma equal to constant. Suppose this is K. Now P to the power 1 minus gamma, P to the power gamma equal to another constant K. So this is the relation. So if we write for two situation, P1 1 minus gamma, T1 gamma equal to P2 1 minus gamma, T2 gamma. This is the relation between P and T. Between P and T at adiabatic process equal to this. If you cannot remember this formula, then you remember this equation. You remember this equation and this equation. Just eliminate V from this equation. V equal to nRT by P. Put here. You get the relation between P and T. Now to relate between volume and temperature. Now relation between volume and temperature. Put here nRT by V into V to the power gamma equal to constant, suppose K. So V to the power gamma minus 1 T equal to constant, another constant K1. So we can write for two cases 1 and 2. Now what is the relation between V and T? P and T, P into V. The relation is here. So relation between P and V is P1 V1 gamma equal to P2 V2 gamma. P equal to constant. So we get different relation between V and T, P and T, and P and V. Isothermal graph and adiabatic graph. Slope of isothermal graph and adiabatic graph. So P into V equal to nRT for isothermal and P into V to the power gamma equal to constant for adiabatic. P into V to the power gamma equal to constant for adiabatic. So we now we want to calculate the slope of the isothermal graph. So PV equal to nRT, PV equal to constant, isothermal, this is constant. PV equal to constant, graph is P, this is V, PV equal to constant, graph is this way. Now if we calculate the slope P by V, so PV equal to constant. Now dP into V plus P into dV equal to 0. If we differentiate both sides with respect to if we differentiate both sides, this we get this dp into v equal to minus p dv. So dp by dv, we know slope equal to dy by dx. Here y is p and x is v, so dy by dx is the slope of the tangent of the graph. Now here dy by dx means dp by dv, so dp by dv equal to minus p by v. Slope of isothermal graph, the value is minus p by v. If we draw the tangent, then slope is negative, so slope is negative. From this we get the slope is negative. Here also we see that the angle is greater than 90, so angle is greater than 90, so slope is negative. Tan theta is less than 0 as theta greater than 90 degree. So this is negative, this also from graph we see that this is negative. Now for adiabatic process, p into v to the power gamma equal to constant. If we differentiate both sides, dp into v to the power gamma plus p into gamma v to the power gamma minus 1 dv equal to 0. So dp v to the power gamma plus gamma p v to the power gamma dv by v equal to 0. So gamma, so take common v to the power gamma, we get dp plus gamma p by v dv equal to 0. So dp by dv we get minus gamma into p by v. This is the dp by dv is slope of adiabatic, so minus gamma into slope of p by v will be slope of isothermal. So we have proved that slope of adiabatic equal to gamma into slope of isothermal. So this slope is more steep. Of adiabatic equal to gamma times of slope of isothermal, that is adiabatic graph becomes more steep. Adiabatic graphs become more steep. That is, if we draw the two graph p versus v during expansion 1 2, so one is isothermal and 2 is adiabatic, because for at a constant particular value of v, suppose this is v, graph slope of this is this and slope of this is this, so this slope is more steep, than this. So if we extend the graph, so from negative side this value is less, this value is more, from negative side this value is more than this value. Theta, this is adiabatic A, theta isothermal, so theta adiabatic is greater than theta isothermal. For negative side this slope is more than this slope, so the two become adiabatic and one become isothermal. During expansion, so during expansion when this graph becomes this is volume increases, so during expansion graph of adiabatic is more than graph of slope of adiabatic is more than slope of isothermal, negative slope obviously. If we draw p versus v during compression, suppose this and this, if we draw the two graph, this and this, now what is this is become 1 2, this is become 2, this is 1. This is 1, this is 1, this is 2. Here this is isothermal, 1 become isothermal and 2 become adiabatic. That the graph will reverse, because if you put this and this is isothermal graph, this is adiabatic. Suppose at point, at a particular value of v, this point and this point, we take this point and this point, so slope of this will be this and slope of this at this point will be this. Now this value theta adiabatic is theta isothermal, theta a is greater than theta I, so here negative slope, we take the angle from this clockwise direction, this way, so here negative this slope is represent negative slope, this slope represent negative slope. Now here negative slope, that is adiabatic, slope of adiabatic is more than slope of isothermal, so when compression take place, this become adiabatic, this become isothermal. And if anticlockwise, if this rotation is anticlockwise, then what is net work done? Net work done is positive or negative? Net work done is positive or negative? How can we calculate? Now this process moves in this way. Suppose this is 1a 2b. During process 1a2 process, the volume is decreases. During 1a2 process, volume decreases. That is, work done is 1a2 is volume decreases by negative work done. Work done is negative. Suppose this is minus w1. Now during this 2b1, volume increases again. During 2b1, volume increases again. So for this work done, 2b1 plus w2, volume increases, so work done is positive. So during this work done is negative. Now we know the area of PV diagram. Represents the work done. So suppose this is BC. So area of 1A2BC equal to W1. W1 equal to area of 1A2BC. Area of 1A2BC equal to W1. Now what is W2? W2 equal to, this is negative area. W2 equal to area of this, area of 2BC1, area of 2BC1, this is W2 equal to net work done equal to what? This is more negative, W1 is more negative. Suppose this is value minus 10, this is value plus 6, so this is negative. That is, net work done for anticlockwise direction, net work done is negative. Net work done is negative. Now for cyclic process, A to B, B. Now for this process, during work done 1A2 process, positive work done, because volume is increases. 1A2 B, CD. 1A2 process, this is for 1A2. This is the area of 1A2 CD. Area of this area is more than this area. Now for W, this is positive work done, and for 2B1, this is the area of minus area of 2B1 DC. 2B1 DC, this area is less than this area, so net work done equal to, suppose this is W1, this is minus W2, So W1 minus W2, as this is more, suppose this is 10, this is 6, so this is 4, that is positive. So work done is positive for clockwise direction. So if we want to calculate the pressure versus volume in clockwise direction, the net work done will be positive. For anti-clockwise, net work done will be negative. Now, so from this calculation we see that net work done for a cyclic process equal to area of this closed system. Also we see that net work done equal to net work done for cyclic process. Net work done for cyclic process equal to area of closed system, area of closed diagram or closed graph. Area of closed diagram or closed graph equal to net work done for cyclic process. Student, this is the end of the class today. For the theory of heat engine, refrigerator and Carnot engine and more important problem in thermodynamics chapter, watch my another video. Thank you.